Okay, before we do any simulations this week, we need to briefly talk about a few more electrical components that we'll be looking at. The first one that we'll be looking at is something called a diode. And I've just drawn the shape of a diode here. And there's a couple things we need to be aware of with a diode. First off, it's something that we've probably heard. You've heard this before. You've heard something called like a light emitting diode. We all know what that is, or if you don't know what that is, you'll know the abbreviation here as soon as I write it down. LED. We know LED lights. That just stands for light emitting diode. So it's a special type of diode. But I want to talk a little bit about what a diode looks like as far as the characteristics, and then we're going to use that so that when we simulate some circuits with diodes, you can actually see the behavior and understand what's going on. So the first thing here is without going into any real details, is a diode has a current voltage relationship. So on the y-axis is current, on the x-axis is voltage. Now this is not going to be drawn to scale precisely, but the characteristics look like this to some extent. And the idea here is that this, depending on the diode, this point right here is, 0.6 to maybe 0.7 volts. And so in some respects, a diode, you can kind of think of it almost as a switch, where if you have positive voltage on it, it's going to allow current to go through. But then if you have negative voltage, it's not really allowing current to go through. You might say, well, wait, there's a little bit, and except that this is really this current, this value right here, that's this current, is like usually 10 to the minus 12th. So 10 to the minus 12th amps. Yeah, that's pretty much zero, but it's a little bit here. And you might say, well, wait, at some point it looks like there's a lot of current going through if I put a negative voltage on, but that's what's referred to as a breakdown voltage. And this is for, this can be anywhere to 50 to 100 volts. So again, you'd have to put a lot of voltage on there to get to that point. So really you want to think of it almost an easier, more ideal way of thinking about a diode. And again, it's not, this ideal way of thinking about the diode is not accurate, but it's an easy way to think of it, is that we have no current when we're less than 0.7 volts, and then once we hit 0.7 volts, we can basically get as much current as we want going through that diode. So that's kind of where it's acting as a switch. It's, quote, off over here, and then it's on over here. All right, so that's one aspect of it. Now, the particular diode we're going to be looking at, because we're going to be looking at doing some simulations for some power supply circuits, we're going to be looking at a special type of diode that's called a Zener diode. And so the Zener diode symbol looks very similar, except there's these little kind of up and down things here. Now what's different about a Zener diode is actually designed to be run backwards. It's designed to be run backwards. And so, well, what do I mean by that? It's designed to be run backwards. Well, the V breakdown for these is much smaller. In fact, a lot of times, a couple of ones that we'll be looking at, the V breakdown is going to be 5.1. Now that's not for all Zener diodes, it's just for the one we're probably going to be looking at. You can have Zener diodes that have breakdown voltages of 9 volts, 2 volts, etc. And it's really depending on the application, but these can be used to build voltage regulators. Now, this is building voltage regulators with what's called from discrete components. There are other ways, and we'll look at this next week. I've decided we're going to do this week and then next week for some more simulation, and then we'll move into layouts. The other one you can look at here is where you can get chips for regulators. And an example of a chip that's a regulator is an LM317. Now, I'm not even going to do a circuit diagram necessarily for that, because that really is just the LM317. I'm just going to even just write a box for it here. It's basically got an input, an output, and I believe they refer to the third pin as the adjustment. And the 317 is something we'll look at, but that particular circuit there, this is actually, if you were to pick one up in the lab, this is not like a single device. It's got multiple transistors and diodes built inside it to actually act as a regulator. Okay, so what are some of the other components we're going to look at today as well in our simulations? Well, the other one we're going to possibly look at two others here, is a capacitor. And a capacitor is really just an energy storage device. And its particular current and voltage relationship is a little bit more complicated than it is for a resistor. You'll learn a lot more about them in your circuit analysis class here. But if I just have a voltage here, I'm going to write it lowercase here because voltage across the capacitor is related to time. And so since it's AC because it's related to time, I'm writing them in lowercase. Typically, capital letters are reserved for DC, lowercase are for AC. And so the current through the capacitor is equal to the capacitance, and then some of you will know what this is, others of you will not, and that's okay. We don't need it for this course, but it's equal to the current of the capacitor is equal to the capacitance times the derivative of the voltage. And that's what this is right here. This is the first derivative of the voltage with respect to time. Now, we can understand these a lot easier without having to go into all those specific details. And let me show you an application on why we want to use a capacitor. So let's see here we have, and this is a chip we'll look at next week here. Let's say we have what's called an op-amp. And an op-amp is stands for operational amplifier. Now, as an op-amp, you're going to have, I'll just say this one here has 8 pins on it, and that's kind of a typical one. Some op-amps have more than 8 pins, but a typical thing for an op-amp is that it has 8 pins. Well, here this is like positive power, and here is negative power as far as for power supply for it. An op-amp needs power. Now, it doesn't necessarily need both positive and negative power. You can use just positive power, but we need some kind of voltage applied here. Now, what we could do is we could try and hook this just up to our power supply, our DC power supply, just as is. And we could also simulate this and hook this up to our, and I'm drawing it upside down to represent negative voltage. Although actually we won't be doing that in our circuit diagrams when we're simulating, so let's just do, and so for instance this might be negative 12 volts and this might be positive 12 volts. Now simulation purposes, you can just have these wires connected up and the power instantaneously gets to the op amp, and you can pull as much current as you need from that power supply, and everything's all fine and good. But reality doesn't happen like that. And so this is going to be a somewhat exaggerated example, but it's true. Now, instead of imagining connecting it up for simulating, let's imagine that we're actually connecting this up, physically connecting this up. So this is going to be on a board somewhere, a PC board. And let's say the power supply is, let's say this board has a shape. Here, I'll do a different color for the board shape. Let's say this board, I'm going to do blue for the outline of the board, the circuit board. So this is like the circuit board. Okay, and then let me erase this here. Okay, so this is the outline for the circuit board, and I put the chip right there. Now, my power supply might be all the way over here. So this is my power. And I might have plus 12 volts here, minus 12 volts here, and then ground. Now, I have to run a trace then all the way up here into here. I know I just erased what I drew, but here. I might have to run a trace all the way up here. So now we're talking about a physical board. We're not talking about just a simulation. So I'm running a trace all the way up there. And then I'm running a trace for the negative voltage all the way over here. And you might say, well, that's still not that far. Well, yeah, it's really not that far. But we're going to have some kind of signal coming into this op amp on one of these pins, and we're going to be maybe amplifying it. And depending on the frequency of this signal, we might need to be able to switch from positive voltage to negative voltage and back and forth pretty quickly. And so we might have to be able to pull current, pull energy all the way back from the power supply. So in other words, if I need a lot of energy because I'm switching the signal from negative to positive, right now it's got to go all the way back to the power supply to get that energy. So it's got to travel this whole trace to get there. But if instead I put in here a capacitor here, what happens? Okay, when I first turn this on, this capacitor will charge up. All we need to know is it's going to charge up and it's going to store some energy for me. So then when I need to switch from that negative to positive voltage real quickly, instead of having to go all the way back to the power supply to grab that energy, it can grab that energy from this capacitor right here and then do the switching, and then basically you say, okay, well wait, it's lost some energy here. Yeah, but then the power supply can go back and still recharge this capacitor. But the immediate energy that I need to do my switching is available based off this capacitor. Now, depending on what you're doing here, and the switching speeds and all sorts of other things and filters, you might actually even have more than just one capacitor. You might have a bank of capacitors here. But that's getting into a little bit more detail that you would learn in future courses. I'm just giving you one application of why you'd be interested in capacitors. All right, the other symbol here that we'll be interested in component here. And there's a lot of applications for this component. It looks like a spring, but this is called an inductor. And it's got an inductance L, and then we have a voltage across it. It's an AC voltage and a current that goes through it, AC current. And this one has a very similar relationship, but in this case the voltage across the inductor is equal to the inductance times the derivative of the current. Now again, we don't need to really remember that all that well, but what we're going to be looking at here in either this week or next week is we're going to be looking at, okay, well what about if I have two inductors close together? And I've got other circuitry going on over here. I mean, this is just part of it. So this is inductor 1 and inductor 2. Now, without getting into all of the theory here, just if you're running an AC current through this inductor, an inductor, believe it or not, you can make an inductor using magnetic wire and just making a coil out of it. You know, you can build your own inductors really easily, just getting magnetic wire and wrapping it around a tube. You know, like even a paper towel tube, you can create an inductor that way, or PVC pipe or something like that. So when you run an AC current through this, it creates a magnetic field, and if these inductors are close enough, that magnetic field actually generates a current in this second coil. So again, if we have here, I'm saying we have an AC current, and I'll call this the current going through L1. What that will do is that's going to create a magnetic field. But then what happens is that magnetic field induces, which is a fancy word for creates, a current going through L2. And there's also some other more complicated stuff that goes on. We're not going to worry about all that complication here. And when that happens, as we say, we say that these inductors L1 and L2 are magnetically coupled. And we often drop the word magnetically and we just say that they're coupled. And there's often something that you'll have which is called K. This is the coefficient of coupling. And it's between 0 and 1. 1 would mean they're completely coupled together. 0 means they're not coupled at all. And if they're not coupled at all, then this whole idea that you can get this current being generated is not accurate. And you can force them to not be coupled by shielding an inductor. There's ways you can shield inductors, and sometimes it's necessary to have shielded inductors in a circuit. But we're going to look at the case where they are coupled together, because this creates a very useful circuit device called a transformer. And some of you might know what that is, and if you don't, that's okay. We'll see what it is when we start doing some simulations. And I will give you a little bit of kind of a thing of an application of transformers. If you know, many of you probably have wireless cell phone chargers, or at least if you don't, you know what they are. Wireless cell phone chargers work using a transformer. Basically, you have an inductor in your phone, and you have an inductor that because it's kind of circular usually, those wireless charging stations, and if they're not circular, if they're square or something, there's a coil inside them, and you set your phone down, and got a message from someone there, close that out. Oh, what came up here? Go away. And you set your phone on there, and those two inductors then get close enough together that they get magnetically coupled, and basically you're transmitting the energy wirelessly. And it's pretty cool. And in fact, I have two electrodes implanted in my face to help control a pain condition that I have, a chronic pain condition, and I've got a battery charger in my chest, and that battery charger is charged wirelessly, and I have, it looks like a giant washer, and it's just a circle of inductor coil. So let's go ahead and end this here, and let's get into some simulations.